Okay, so this is cross-compatible encryption adapter for securing legacy Modbus devices. A paper authored by me and my co-author and a very cool professor, Dr. Sriram. So I think 21st century started with this attack in Australia called Maruki water service attack. So what happened in that, the hacker seized the communication between remote terminals and control systems. Now, as much as I understand that I have studied about that, it is NIST has defined this industrial control systems as critical systems. So that's why these kind of attacks are really dangerous for us. So next is the Stuxnet attack, which was uncovered in 2010. So what happened is, in the first, the CIA and potentially the Mossad from Israel, they attacked against the Natanz nuclear facility and seized the nuclear power plant. And this was done by, injecting malicious payloads into PLCs and Modbus devices. So yeah, this was caused unprecedented damage. And since this was a state-sponsored stuff, so there is not much about to talk about it. Then there is a black energy attack. The war is going on, but it started back in 2015 when Russian hackers tried to go into power outage into Ukrainian power grids. So yeah, these three attacks were really devastating for the critical systems, and work needs to go into that place. So what we find is the issue is not with any other thing, but it's the Modbus protocol. There are issues with a lot of cyber physical systems, but one of the major issue that we pointed out is the Modbus protocol itself. So the Modbus protocol is like, it's 2025, and this Modbus protocol was developed in 1971 by Modicon, which is now Schneider Electric as we know it. So it is now the de facto standard for industrial control system and have been well established. So it can't be removed. And just look at this. This is like, it's one of the most easiest, as simple as that protocol that can be found. It's like it has a slave address, a function code, data, and cyclic redundancy check. Just second year or first year bachelor's level stuff, and it is used into our industrial control systems right now. Our healthcare depends upon this protocol, and this is open. We have no encryption, we have no integrity checks, no authentication. Anyone can join the network, and every kind of stuff is happening out there. So what we did is first categorize the attacks which is been due to Modbus protocol. So it is reconnaissance attacks, response and measurement attacks, command injection attacks, denial of service attacks. So these are the four types of attacks which are mostly happening in here. So industrial control systems are backbone to our living. Securing it is not optional, it's essential. And if we don't, economy crumbles, human lives are affected, healthcare goes down, and unfortunately people die. That's the reality of that's the reality of not working on this point. So the issue, what we identified is, the issue is not the lack of protocols, it's the issue of economic constraints. Like, we have much better protocols. We have SSL, we have TLS, encryption whatsoever, quantum resistance algorithm. But buying new systems is expensive, installing new systems is expensive, installation takes time, downtime. We can't suffer like healthcare goes down, power grid goes down or anything. And manpower is tremendous. And even if we get over this and make a whole industrial control system new, cyber attacks are advancing faster. We have to upgrade it again and again and again. So what we did is focusing on securing existing infrastructure with add-ons. Just keep what it is as it is, and let's add some add-ons to get with this. So so we propose the cross-compatible encryption adapter for securing legacy Modbus devices. The legacy word is very important. We are focusing on systems which are built in 1970s and 80s and 90s. So what we did is, we proposed a smart industrial control system. So remove the adapter part. We have all the hosts connected in a star topology, which can be boiled down into master-slave architecture. So these adapters are something that guard the hosts from the untrusted networks. So whatever is happening into the untrusted network, we believe there are tapping attacks, wiretapping attacks, reconnaissance, and all is happening on that side. And we let the adapters own the network and focus on securing it. So this is something which looks like when you install the adapter. So it has a plain Modbus packet, receives and gives, and just gives out encrypted data and everything. So it translates the Modbus RTO into encrypted data stream, but it's much more than a traditional gateway. There are currently devices which do this, but it is much more that I will show you. So this is a high-level architecture, what the single adapter unit looks like. So there is a real-time ARM processors. You can use any processor you like as dependent upon which type of control system system you're dealing with. So if you have a critical system, you can have ARM V8 processors, really expensive processors, but good for like having it for fast performances. But you can have M0 processors, really cheap, $2 to $3, and it can still work. So we have so important part is we have a secure flash memory here, and we have a flash memory with RTOS configuration. So RTOS is a real-time operating system which focuses on real-time encryption, decryption, validity, and all those things. And secure flash memory is important. So what it does is every host ID, like in Modbus slaves have ID assigned to himself. We have an adapter ID which is an ECC elliptic curve cryptography public key which identifies each adapter differently and identifies the remote terminals. So that's why we employ high performance, cost efficient ARM processor. The cost efficiency is much more important in this case. So the outcome of this is, first of all, encryption. Again, everyone does that. Current gateways do that, but those gateways are big. And what we are have built into our test bench is, it looks like this one. The size of it is as similar to this laser pointer. So all Modbus protocol, all Modbus packets are encrypted with receiver's public key. No host can decrypt it. That's pretty usual stuff we were doing. The important part is the integrity part. So authorized devices have the public key of the receiver. Everybody is distributed with the public key, and receiver decrypts using private key. And if message is valid, the source of the packet is valid, because this is something that we, I call this network a self-aware network. Every adapter is aware of each other. So everybody have the public key of each other, and they have their own private key. So everybody is able to identify which kind of, who is sending the message. It's encrypted by public key. If you are not, if the adapter itself is not being able to decrypt it, then again it's a we would say a false packet, and you should not accept it because it's not yours. You can't decrypt it by your private key. If there is a person in the network who knows the private key, okay, he will decrypt it and have it, and we have it, and we have the packet decrypted. Third thing is authentication. Authentication is each other public keys are known and self-private keys are stored securely, as you saw in the secure element itself. Adapters are programmed initially to store public keys of other adapters. So what we are doing here is, in our test bench, we have a docking device. You first get all these small adapters, you just plug it into it. You program it one time. Everybody knows about each other. Everybody has their public key, private key, everything. And you can remove it and just get this pin out, just put the adapter in, that's it. It's a $30, $40 device and secures your whole control systems. You can have hundreds of PLCs, no worries about getting hundreds of new PLCs. Just get one of these adapters of $10, you're like $500 investment, and it's now secure forever. Then all adapters send random packets to adapters and wait for responses. So this is something, a secure mechanism. It's a self-immune system which tests for it. Again, I can't explain the whole algorithm here. It's well defined in the paper. You can go through it. So what it does is, everybody sends random packets to each other and check if, okay, is everything okay right here? Do we have each other's public key and private? Can we decrypt it? Can we do it? And if it's okay, then it goes on. Again, the algorithm has been mentioned in the paper, so you can go and just dig around it. And most of the code that we do is open source on GitHub. Anybody can access it. Even the lecture has been recorded, so you can view it afterwards. Slides will be uploaded also. Important thing, last thing I would say, updating the adapter, firmware updates by wired channels and wireless update, which is a future work. Important thing is, we have a control system which can be updated in the future, so that in future when attacks are coming along, we can be immune to this. If we find an encryption flaw in the ECC part, we can update the ECC part just enough. Let's go with our own work. Then future work and conclusion. Now, most of the reviewers told us that this part should be included in a future work, but fortunately, I'm done with doing most of the stuff here, so you can ask about these questions: upgrading into radio frequency channels, wireless firmware updates, practical implementation for testing, optimizing overheads. A very important part has been comprehensively given in my paper and has been implemented right now, will be in my next paper, and recommendations for hardware selection, important for economic constraints. So yeah, that's it.
Thank you so much. The presentation was really energetic. Yeah, so if you have any questions.
Aditya,
Yeah.
So you had mentioned like you are using one adapter. Suppose you have one master and multiple slaves, like 100 of slaves. So in that situation, what you are doing? You are connecting every adapter and every devices, or you just connected one as a gateway, and after that you are sending the data in the cloud platform.
I would say the adapter itself is a paired with that Modbus device. So every slave has to have its own adapter. Adapter is like an identity to it. So it guards that device. So for the device itself, it's an 1970s system, 1980s system. So it uses the adapter as its new identity. So for it, the control system is like sending the same Modbus packets. There is no issue into that. But as soon as this adapter is introduced, it's like a virtual network for that device. So what this does is for it Modbus packets are coming along, going along, but for the adapter is actually guarding it from all the attacks. So that's what. So you have to have 100 of adapters into that. But again, the adapters are cheaper than the PLCs themselves, which cost more than $1,000. So yeah, that's it.
So one more question is like that. Suppose you said I will like connect adapter. So on the basis of you cannot like you can dump the code inside in the microcontroller. That is one another option is there. So why you are not going for that perspective?
Can you repeat it, please?
Suppose now you are using an adapter. Okay. So same code is already inside in that. Suppose you are doing that stuff in the there. So you can dump that same code in the microcontroller also. So that is also enough for securing that your Modbus protocol.
Yeah, but again, you have to change all the PLCs in that case. We don't want to do that. That's the part of this problem, that we don't want to change the industrial control systems and PLCs. That's why we are introducing adapters into that. Yeah, that answers your question?
We can meet later.
Yeah, sure, we will.
Yes, ma'am.
So you have different kinds of attacks that these are subject to. So are there specific kinds of attacks that your setup is customized toward?
Actually, that's why we categorize the attacks in the first place, so that we can be focusing upon these attacks. And in the paper itself, for each attack, we have provided why our adapter does that. Why our adapter is literally immune to these attacks. Like security is always just making harder to attackers to attack, but in this case, it's like solid part of it.
Empirical results for each of these attacks and how your protocol
Yeah,
prevents these attacks?
Yeah, we actually did this after submitting this paper into COMSNETS. So for now, yeah, that work has been done, circuit has been implemented, everything in my test bench, and we have the empirical results which will be published into the next paper.
I see. I was looking out for that and was hoping to see it. So that's an important thing to have.
Yeah.
But I guess, yeah, what is the success rate under these different attacks?
Yeah.
So you have that now. The
Yeah.
empirical results.
Yeah, sure. I have it right now and will come in the next paper.
Nice.
Any more questions? Okay, so I have one. So from the future work, like already you have implemented that with the radio frequency channels, you are like experimenting with these channels, RF channels.
Yeah.
So what are the difficulties that you are facing with RF communications?
Okay, this is a very nice question, because in my recent paper also, in my next paper, I have literally a section about future works. My all papers have future work section. So radio frequencies, I have implemented radio frequencies for differentiating the channels between what we are doing. Emergency systems have different because they are time critical. Monitoring is different because they are flooded. And the third thing is control, which is critical again because injection should not happen. So all these radio frequencies can be jammed, which is one of the biggest issue that I'm facing. Jamming is one of the issue. And radio frequencies don't have any boundaries. It goes outside your industrial control system. So sniffing is one of the problem. Then fake data injection, beacon injections are really big issues that we are tackling. So yeah, we have found that we can, I've talked with a lot of guys about this, and they are like use ML models to sniff for this and jam that band and all. So this is something that I'm facing right now.
You are exploring.
Yeah,
Great.
a lot.
Yeah, so we thank the speaker.